Hello, I am Rahul Gopinath. I am a postdoctoral researcher at the CISPA Helmholtz Center for Information Security, Germany. My main focus is on static and dynamic analysis of software. I earned my PhD in 2017 from the Oregon State University in nutrition analysis, specializing in evaluating the quality of test suites and test generators. And today, I am going to talk to you about the science of fuzzing. So, what is fuzzing and why do we need it? The story begins a few hundred years before the dawn of the first millennium. There was a crisis. Sanskrit, the ancient language of Indo-European nomads, was undergoing a transition from a fluid set of dialects to a cohesive urban language, a language of logic, philosophy, and science. A language cannot serve as the language of governance, and especially philosophy and science, unless there was an agreement on what was being said. Hence, there was a push to unify, to formalize the language. And there were many attempts to capture the numerous rules of Sanskrit, and most of these were ad hoc. The turning point came with Ashtatyayi or 8 chapters by Panini. Ashtatyayi transformed the various ad hoc rules of Vedic Sanskrit into the modern grammar of classical Sanskrit. This grammar made it possible to rely on the precise meanings of a given text and to build things on top of it. And this is, of course, old news. And we are now 2021, 2.5 millennia later. The world is governed by software and we face a crisis. As you all know, our software is growing in complexity. And this is the growth in size of Linux kernel year after year and release after release. And of course, the number of vulnerabilities found also keeps up with the growth of our systems. And these vulnerabilities can be exploited by malicious actors, compromising the security and privacy of our users. And the best way to make our systems robust is extensive testing. And automatic testing, especially fuzzing, can help here. Now, fuzzing is fairly simple. The idea is that no system should crash when given any input. So, fuzzers try to generate random inputs that can induce crashes in the system under test. If you wish to learn more about fuzzing, especially how to build practical fuzzers that can be used in the real world, I have co-authored a textbook on fuzzing that teaches students how to build effective fuzzers. The fuzzing book is a first textbook for students who are new to fuzzing. And it takes the beginning student through writing basic fuzzers and using them to fuzz non-trivial applications such as browsers. We also introduce advanced features such as instrumentation guided fuzzing, grammar-based fuzzing, symbolic execution, and tracking information flow to students by building each technique from the very same basic building blocks. And the complete book is available online as a runnable Jupyter notebook. That is, students can simply open the notebook, make the changes as they wish, and see the effect of their changes immediately. And we have used this book for teaching courses in fuzzing and software testing at Saarland. Now back to our topic. Crashes are not the only automatic checks possible. You can also look for memory bounds violation, safety violations, privilege escalations, etc. Now the nice thing about fuzzing is that it requires little human evidence, human guidance, both in terms of inputs as well as in terms of the checks required. So here is how we fuzz. We generate a random input, which is then fed into the program. If the program crashes, we have found a likely vulnerability because the input was unexpected by the program. That is, there was a logical flaw in the program that could be subverted by the attackers. Fuzzing is effective if the fuzzer can generate sufficient inputs that can exercise all parts of the program. Unfortunately, random fuzzing assumes that all inputs are equally useful. However, real-world programs often contain boundary conditions that split the program input space into unequal parts. For example, in a method to check for prime, the numbers until 3 are on one side of the boundary and they traverse a different path than other numbers. Now, the most popular way to overcome this issue is by use of instrumentation. That is, we insert probes into the program that extracts the path taken from the program. And this runtime information is used to guide the input generation. And here is how instrumentation guided fuzzing works. We start with some seed input which traverses a path through the program. And this path is captured by the instrumentation. Then we use the instrumentation to guide our input generation for a new input that traverses a different path. And there are two main variants of instrumentation guided fuzzing. The first is coverage guided fuzzing and the other one is constraint solver directed fuzzing. In coverage guided fuzzing, the idea is to simply wait for inputs to initiate a new coverage. Any input that produces new coverage becomes a seed input. And a population of such seed inputs are mutated in the hopes that this will lead to further exploration of the program. And AFL is an example of an instrumentation guided fuzzer. It uses structural coverage obtained to generate complex inputs. Now, the main issue with coverage guided fuzzers is that formats often require specific constant values to be present in the input, the so-called magic bytes. And these are very hard to produce by simple random chance. For example, it is very hard to generate keyword values such as catch, continue, etc. by simple random generation. That is, coverage guided fuzzing is fast and general, but it is not effective against all programs. In particular, coverage guided fuzzing performs very poorly against parsers. The other major variant of instrumentation guided fuzzer is a constraint directed fuzzer. The essential idea here is to generate inputs, collect the symbolic constraints along the execution path, and negate typically the last constraint and solve the negated constraint to generate a new input. And the PEX concolic execution engine from Microsoft is a concolic fuzzer. Now, the problem with this approach is that parsing a format often have an extremely large number of paths through the program, all ending up in failure. And this is called the path explosion problem. Concolic and symbolic fuzzers hence do not do well with parsers. That is, concolic and symbolic fuzzing can be applied to all programs, but it slows down tremendously when there are multiple paths through the program. That is, instrumented fuzzing is really bad against any kind of structured data. The problem is that it is difficult to generate inputs that conform to complex input specifications, and we cannot reach the internals of the program without passing through the parser first. Now, given that we need to get past the parser, the final strategy has been to simply encode the constraints of the format into the fuzzer itself. This way, fuzzer is fast and effective, And CSmith is an example, and it targets C compilers. The trade-off here is generality. That is, CSmith can only ever fuzz C compilers. Further, it can only explore the parts of the input space it knows about. That is, no extension to C can be explored. This is obviously not very scalable. That is, the holy grail of fuzzing has been to build fuzzers that are fast, effective, and general. And the input parsers have been a major thorn in these efforts. So, a large number of fuzzing papers in the last decade have been focused on getting past the parsers. Unfortunately, what people have been doing so far is to pile heuristics on top of heuristics to get fuzzers past the parsers somehow or the other. And the problem with this approach is that it is very ad hoc. Each program requires their own adjustment, and it is often not clear why something worked or did not work. Unfortunately, it is often very difficult to identify and extract the interesting pieces of a fuzzer and apply it on another. And most fuzzers are not built for easy reusability of parts. And the problem with such monolithic architecture is that it is very difficult to understand the actual new contribution of innovation in any given fuzzer. It is often not clear if the fuzzer achieved its success because of the highlighted technical idea or because of some unseen optimizations. So, fuzzing has been more like alchemy at this point. So, how do we transform fuzzing from alchemy to a science? And this is what I have been focusing on. The main problem with instrumented fuzzing has been parsers, which implement some input specification. So, if we have the input parser or the input specification for the given program, we can easily get past the parser. Now, what is a grammar? A grammar is a formal language description that specifies how an input is constructed. And there are different kinds of grammars based on the power of the grammar to construct increasingly complex inputs. The simplest is regular grammar, which can construct simple inputs that can be matched by state machines, that is, regular expressions. The next is context-free languages. These require a stack attached to the state machine for recognition, and these are called push-down automata. And then we have recursively enumerable languages, which can be matched if you add one more stack to the push-down automata, and these are equivalent to Turing machines. Now, of these, context-free languages provide a good balance between the ease of parsing and generation and power. So most programs use context-free grammars as the base grammar. So we'll be focusing on context-free grammars and corresponding languages. So here is an arithmetic expression grammar, which is a context-free grammar. And a context-free grammar is just like a procedure definition in programming languages. We have a number of keys and associated definitions. And each definition contains multiple expansion rules. And each expansion rule defines one way to expand the non-terminal and contains terminal and non-terminal symbols. And each non-terminal symbol in turn has their own definitions. And terminal symbols are simply basic alphabets of the input. And these grammars can be used for parsing. For example, given the arithmetic grammar, we can parse the input 8 by 3 into 49 into a parse tree. But more than that, These grammars also allow us to generate nearly an infinite number of varied inputs, all conforming to the input specification. That is, given the input grammar, we can now go beyond the parser and reach deep code paths. And the grammars can also be very efficient in generating inputs. That is, we can compile the grammar to produce a fast input generator. And we can do more than compiling. A grammar fuzzer randomly chooses non-terminal expansions to generate inputs. And we can consider this stream of random choices as opcodes for a virtual machine. And we can transform that into blazing fast machine code, as we show in our paper on building fast fuzzers. Now, grammar-based fuzzing is not a new idea. A number of fuzzers use grammars to generate inputs. The bigger question is, where can we get these grammars from? The actual formal specification for a program is notoriously hard to obtain. Let us take the ideal case, when there is a well-known standard for the format. Unfortunately, even in this ideal case, we also have to contend with buggy implementations or extra features that the developer decided to include. For example, there are a number of GCC extensions to a C language which are not specified as the formal grammar. And then there is also the built-in error tolerance for inputs in a number of programs such as browsers and parsers that make it accept invalid inputs in the name of convenience. Here is an example. We all know about JSON. It is quite a simple language that can be specified in the back of a business card. Unfortunately, even such simple specification is notoriously hard to get right. And here is an evaluation of whether JSON parsers conform to JSON specification by Surrey. Y-axis lists the various parsers and x-axis are the various common misimplementations. And these are the results of the evaluation. The green color represents places where tests pass. Variations of yellow and red represents where the test failed, and blue represents where the specification was underspecified. Ideally, it should have been completely green, but you can see that almost no parser actually implements the specification correctly. Unfortunately, in most cases, there is not even a specification. And even if programmers started with a formal specification, it can get out of it really fast. Essentially, for handwritten parsers, documented grammars are untrustworthy. The problem is that the effectiveness of our fuzzing is directly dependent on the input features that were present in the grammar. Any missing input feature is a blind spot. So where do we get the grammar from? Our key idea is that handwritten parsers written in a recursive descent fashion already encodes the grammar. And we present a technique that can extract such grammars from given programs. And our technique first extracts the dynamic control dependence trees from given sample inputs that cover all features of the program. And then it combines these trees into a general grammar. So what is a control dependence graph? A control dependence graph is a graphical representation for the program where each statement gets a node and there is a directed arrow between the control dependent nodes. A statement B is control dependent on statement A if A determines if B executes. A dynamic control dependence tree is similar to a control dependence graph, except that we use statement executions. Essentially, each executed statement in a program is a node in the tree. And each statement execution is control dependent on the statement that caused it to execute. And to this tree, we attach input characters. Each input character is attached to a leaf node that accessed it last. And this makes the dynamic control dependence tree a parse tree. And here is an example parse tree for the arithmetic expression 9 plus 3 by 4. Now there is a bit more to be done to make these parse trees accurate. In particular, you may notice that not all nodes that are named while are compatible with each other. That is, we can't replace a number with an arithmetic operator and expect a valid input value. So we will see how to deal with them next. That is, given these trees, we need to identify which nodes represent the same non-terminal in the grammar. For example, here we may not be sure if the two while nodes are compatible. So what we do is to swap them and check if the resulting input is valid. If they are, then they are compatible. That is, they represent the same non-terminal. And we represent the compatible nodes with the same color. Here is another example. We check if the two parse expression nodes are compatible. Here, instead of swapping, we simply replace the larger one by the smaller one. If the nodes are compatible, simple replacement should also work. And since this produces a valid input, both nodes are compatible. So they represent the same non-terminal. And here is an example when two while nodes are not compatible. That is, the two iterations do not represent the same non-terminal symbol. So we can now combine the parse trees into a general grammar. And here again the colors represent compatible nodes. The idea is that children of a node form the expansion rule of the corresponding non-terminal. So the parse expression node has two possible expansions from this tree. Similarly, we can collapse the rest of the tree for a preliminary grammar and the remaining forest. And from this, we can abstract the final grammar. So here is the final recovered grammar from the arithmetic expression parser that we saw earlier. And of course, the grammar generates the expected input string. Another example is the JSON grammar recovered from microJSON. And our technique, which we call MIMID, is lightweight and can be applied for a variety of parsers. The grammars produced by MIMID are all well readable. Now, what we have so far is a dynamic, context-free approximation of the actual specification. Interestingly, we can also run MIMID statically, producing an over-approximation. Now, why do we need such an over-approximation? The problem is that many of the systems that we want to fuzz, such as IoT and embedded devices, cannot be run under instrumentation. And if we want to reverse engineer their interfaces, we have to rely on static analysis of their program dependence graphs. In fact, this is one of our current projects. Now we come to the next issue. That is, for us to produce such grammars, the inputs that we start with should cover all features. However, producing such inputs is difficult. Why not use the seed corpus as instrumentation-based fuzzers such as AFL does? The issue is that when we exclusively rely on seed corpus, the variety of inputs that we can produce is determined by the variety of the seed corpus. This can lead to blind spots. So we cannot really exclusively rely on seed inputs. So what should we do? The key idea we had was to get feedback from the parser. A parser typically processes inputs one byte or one character at a time. So we try to construct valid prefixes that are accepted by the parser as incomplete, which eventually lead to complete inputs. So let us say we had a program without specification that we want to generate inputs for. We start with an empty string that is fed directly into the program, which is quickly rejected as incomplete. Our instrumentation tells us that it encountered an EF error while processing. So we add an arbitrary letter A to the input, which is again fed into the program, and this is rejected as incorrect. But before rejecting, the last character was compared with different values. So what we do is to choose one of the compared values randomly, here an open parenthesis, and replace the last character in the input string with that value. Then we add one more character randomly, here 2. And the system continues this process until we reach the close parenthesis. Now the system responds that the input is valid and the complete string is parenthesis 2 minus 94. This technique, as you can see, effectively turns any parser into a generator, producing high quality inputs without any bias. Unfortunately, this technique is rather slow. So instead of using them directly, we use it in combination with a grammar miner. We use directed fuzzers to explore, then use the grammar mining to generalize, and again use the directed fuzzer to refine. And with these three technologies, our fuzzers can be fast, effective, and general. Now we can mine the first level grammar. So what exactly are the next challenges? Consider how to fuzz an RPC method call to get the stock. Now to fuzz the system, you first need to extract the protocol grammar, the container grammar, the secondary envelope schema as a grammar, and finally construct the RPC call, which may again require specific data structures. That is, there are multiple levels of grammars that we have to contend with before we reach the fabled pot of gold. And Mimit can help us with the first two levels, but the remaining still requires research. I believe that we can tackle this with a combination of Mimit, variable tracing and decomposition, as well as novel string inclusion techniques that we are currently researching. Similarly, if you want to fuzz compilers and interpreters, you need to handle semantic envelopes in the form of variable names and types. In this example, we are fuzzing the C compiler. And if we need to have a valid input file to fuzz, we need to ensure that the types are correct. No variables are used without declaring them, and you pass the correct arguments to the function calls. Here again, we are at the first level. Everything beyond still requires research. And I believe that we can tackle each envelope separately. And Mimit, variable tracing, and string inclusion techniques can all be combined together for effective solutions at each stage. And this would be one of my new focuses going forward. Until now, we talked about the science of inputs. The next part of my talk is about the science of program behavior. Now, say we found a crash. Why did the program crash? we can use delta debugging to minimize the failure-inducing input. However, while the new input is tiny, it still doesn't give you any indication as to the cause of the crash. For example, this input, double nested for, doesn't tell us if the crash happens for any input that is larger than 4 characters, or if the character 4 is somehow important. And a number of such questions. So, can we do better? Can we identify what caused the failure? Indeed, consider these issues from real world projects. Each of them are minimized test cases, and while they look simple, they leave many questions unanswered. For example, are the repeating variables here important? Is the empty object important? Can you have other declarations? Are all parts of the input equally important? None of these questions are answered. So the question is, can we fix that? So our idea was to parse the failure-inducing input into its parse tree, and then we looked at what parts of the inputs can be replaced by randomly generated inputs. Any part of the input that can be replaced by all tested syntactically valid replacements can be marked as abstract. So the technique is to start at the root and replace each node with a randomly generated node of the same kind, one at a time. If the node can be replaced with a random node without causing a failure, then that node is abstract. Here, we can see that only the last EXPR could be replaced by randomly generated trees. So we mark that node as abstract and all other non-terminals as concrete. Then we collapse the tree and leave the abstract node as is. And you can see that our abstract pattern precisely captures the predicate. That is, the failure is caused by double nested parentheses. But is this useful in practice? Here are again the few examples we saw from the real world. This is issue 2937 from Closure, and you can see that we were able to abstract two non-terminals here, corresponding to the variable name and identifier. Issue 385 from Rhino, and you can see that we were able to identify the required common variable names. And we were able to identify that the variable declaration can be generic. That is, it is not relevant to the bug. And this is issue 386 from Rhino. We were able to identify the constraint, namely that the variables have to be the same in this expression. And this issue 2842 from Closure. Again, the variables are required to be the same, and they are all required to reproduce a failure. So, DD set is able to effectively abstract a minimized input that tells us where the problem lies. Now, notice something about DD set. So long as we have a predicate, we can abstract the pattern from the grammar that passes the predicate. This predicate need not be just failures. It can be generic behavior such as coverage of a specific portion of the code, or that the code opens a network socket or a file or closes it or allocates or frees memory or other resources or any other behavior that we are interested in. The only limitation is that we require a precise predicate, and also that we only capture a part of the possibilities. That is, the pattern represents inputs that are similar to the original input. Now, what we have are patterns that indicate causal and general parts of an input. What can we do with these patterns other than simply using them as a hint during debugging? One immediate application is specialized grammars for fuzzing. We can embed our abstract patterns into the base grammar, producing specialized grammars. And such specialized grammars have two useful properties. The first is that any input produced from the grammar will contain a fault-inducing fragment. And this gives us an infinite supply of inputs that will all reproduce the fault. And the second is that the new specialized grammar will detect any instance of the fault inducing fragment if it is present in the input. So that means that we can use our specialized grammars for focused fuzzing. Now the patterns we mine have really interesting properties. They can be combined together with other similar patterns for the same base grammar, producing even more specialized grammars that can be used for focused fuzzing. Now, just to show what is possible, here are our mined patterns so far. We had 2 closure bugs and 2 rhino bugs, all from the same JavaScript grammar. Now you can create a specialized grammar that is guaranteed to generate inputs such that fault patterns from both closure bugs are present. You can also generate specialized grammars that is guaranteed not to produce inputs containing either of these fault patterns. And you can produce specialized grammars where the generated input contains at least one rhino bug and at least one closure bug. In fact, you can go for arbitrary complex expressions and attach any constraints. That is, we can embed almost arbitrary constraints into a base grammar, producing inputs that obey such constraints and corresponding predicates. Now, again, what kinds of constraints are possible? It can be to cover any part of the code or ensure that a particular part of the program is not covered by generated inputs. If a bug is always found with another bug, we can ensure that the inputs generated reflect that. And we can also ensure that a common bug is not triggered in generating inputs by negating it. Now, all these required custom generators previously, which limited their effectiveness. With our technique, such properties can be mined directly from the program and used in combination with other properties. Now, it is very hard to overstate the importance of this research. To understand just one facet, consider lang fuzz, which is one of the most successful fuzzing strategies so far. What it does is to try combining fragments of previously found bugs, producing new inputs that hopefully contains failure-inducing fragments. With our patterns, we can now precisely control what we combine, forming hypotheses about what kinds of failures are expected based on what constraints the inputs were under. That is, we transform the ad hoc approach of combining fragments into a science of focused fuzzing. So, I have shown how we can isolate causative parts of an input, producing generalized patterns capable of reproducing the interesting behavior. Our DDSet algorithm is capable of generalizing as well as decomposing program behaviors, identifying corresponding input patterns. I have also shown how we can combine such generalized patterns to produce inputs that are expected to produce complex behaviors. Now, together, what we have is a science of program behaviors. Now, the biggest challenge involved in verifying program behavior is to determine when a program diverges from the expected behavior. And in a lot of cases, this is easy. The trouble is that some faults may be masked. And of course, sometimes we may not even have a reasonable oracle, as in the case of fuzzers. So how do we flag these failures automatically? One idea is to observe that the variables involved in a failure often have outlier values from the normal observation. So, if we can monitor variables for outlier values, we might be able to flag some failures. In fact, this is the dynamic invariant mining approach used by DICOM. The problem with this approach is twofold. The first is that it is often not clear what an outlier value is. The second is that a typical program may contain numerous variables, generating GBs of values in a single run. And monitoring each of them for outlier values is not very efficient. And we have solutions for both parts. The first is that, as we saw before, is to mine and associate the simplest behaviors with generalized patterns. So we limit interesting behaviors to input patterns we can either specify or mine and validate. For example, the removal of a database table should exclusively correspond to a drop table statement in the input. For the second part, the idea is that many failures are combinations of other failures. An idea from another field, mutation analysis. So, if we can identify variables that are involved in non-failures, we can restrict our attention to them. How do we generate a non-failure? Simply seed faults using mutation analysis and look for changes in variables from the original execution. Once we can identify which variables and invariants to look for outlier values, we have efficient plausible oracles for fuzzing. A related challenge here is fuzzing non-traditional programs such as machine learning models. How do you first say a classifier? Traditionally, the basic methods for fuzzing such systems is either metamorphic testing, where you perturb the data to be classified, or differential testing, where you perturb the input data or use a different model. Now you can see that with this approach, we can go beyond that. We can produce input patterns that correspond to major classifications and check the result of pattern combinations. When we combine the science of inputs with the science of oracles, we get the science of fuzzing that lets you automatically and rigorously evaluate how programs behave. Where do we go from here? One of the troubles with fuzzing is that it is easy to identify numerous bugs and vulnerabilities and overwhelm the developers. And this, of course, has a cost. Developer time is limited, and also you want to move fast and fix it when a vulnerability is identified. So ideally, we want to log both the bug as well as the potential fix. Now, given that we can automatically fuzz, can we automatically fix bugs? And there are, of course, a number of researchers trying to do just that. Now, the trouble with the current approaches is that they are far too simple-minded. They do not yet scale to real-world issues. Now, why is it that they don't scale? One major trouble is that we lack sufficient number of test cases to verify the correctness of our fixes. But we have a secret sauce. With our science of fuzzing, we have a good way to generate numerous inputs and validate them. That is, we can generate good test cases to scale. These combined together can enable better fault localization as well as better repair. So in summary, we have shown how we can mine grammars out of thin air using unbiased parser-directed exploration. The grammars that we extract are well readable and usable for a number of other tasks in software engineering, such as program comprehension and debugging. And indeed, given such a technique, we can generate inputs at the rate of millions per second. And all three forms a fuzzing pipeline that is completely automated. Finally, if we find a bug, we have shown how to automatically generalize its behavior, identify the causal parts, and use it for more rigorous and focused fuzzing. Together, my work can form the foundation for the next generation fuzzing platform. Thank you for listening, and I will be happy to answer any questions.